Welcome to the lesson on logarithm. Let us see what is a logarithm. Logarithms are another way of thinking about exponents. For example, we have that 2 raised to the 4th power equals 16. That is expressed by the exponential equation as 2 raised to the 4th power is equal to 16. Now suppose someone asks us 2 raised to which power equals 16? The answer would be 4. This is expressed by the logarithmic equation log 16 to the base 2 equals to 4, also read as log base 2 of 16 is 4. We have the exponential equation 2 to the power 4 is equal to 16, which can be written in the logarithmic equation as log 16 to the base 2 is equals to 4. Here, both equations describe the same relationship between the number 2, 4 and 16, where 2 is the base and 4 is the exponent. 16 is the number or the argument. Let us look at some more examples on logarithmic form and the exponential form. We have the logarithmic form log 8 to the base 2 is equal to 3. Now can you think of the exponential form for this? Yes, it is 2 to the power 3 is equal to 8. Now let us look at another example. Log 81 to the base 3 is equal to 4. How can you express this in exponential form? Yes, it is 3 to the power 4 is equal to 18. Now the last example, log 25 to the base 5 is equal to 2. Can you think of expressing this in the exponential form? If you have thought this, absolutely, 5 to the power 2 is equal to 25. Now these are the examples using the numbers. Now let us look at the general form. B to the power c is equal to a. What form is this? Is this a logarithmic form or the exponential form? This is the exponential form. B to the power c is equal to a. Now if you have to transfer this into exponential form, how can we represent this into the exponential form? It is log a to the base b is equal to c. Here, this b, which is in blue both the sides, are the base. So when we have that b base in the exponent, when we write it in the form of logarithm, then it will be log to the base b. The c here is the exponent, and also this exponent is also sometimes called as power or also index. So it has 3 names, and this a is the number that we are dealing with, or we call it argument. So here it is, base, exponent and the argument. Now that we understand the relationship between exponents and the logarithm, let's see if we can evaluate logarithms. For example, let's evaluate log 64 to the base 4. Let's start by setting that expression equals to x. Here, log 64 to the base 4 is equal to x. We can express this in the form of exponential as 4 to the power x is equal to 64. In the left hand side we have 4 to the power x. So the 64 also we represent with the same base 4. And when we represent 64 with the base 4, we can write it as 4 to the power 3. Using the exponential law, when we have a to the power m is equals to a to the power n, then m is equal to n. That is, for this equation, Since the base are equal, that means the power should also be equal. X is equal to 3. Therefore, log 64 to the base 4 is 3. Let us look at some logarithmic properties. The first property is the product rule. Log mn to the base b can be expressed as log m to the base b plus log n to the base b. For the quotient rule, log m divided by n to the base b can be written as log m to the base b minus log n to the base b. The power rule says log m to the power p to the base b. So here the argument is m to the power p. This can be expressed as p times log m to the base b. The power of the argument can be taken in the front and multiplied with the log of the base of the argument to the base of the log. In order for the logarithm to be defined, the arguments of the logarithm, here in this case m and n, must be positive, and the base of the logarithm must also be positive and not equal to 1. Now let us look at the example of the product rule. Log 32 to the base 2 can be expressed as log 4 to the base 2 plus log 8 to the base 2, because 4 times 8 is 32. 32 can be expressed as 4 times 2. So we are separating log 4 to the base 2 plus log 8 to the base 2. Here we know log 32 to the base 2 is 5, because 2 to the power 5 is 32, and log 4 to the base 2 is 2, that is 2 to the power 2 is 4, and 2 to the power 3 is 8. Therefore, log 8 to the base 2 is 3. So we have the left hand side 5 is equal to the right hand side 2 plus 3, which is true. Expanding logarithm using the product rules. So how do you think we can expand log 5y to the base 6? Yes, we can express it as log 5 times y to the base 6. So we can write it as log 5 to the base 6 plus log y to the base 6. Similarly, condensing logarithm using the product rule. Now we have two logarithmic expressions added, and the logarithmic expression has the same base, log 10 to the base 3 plus log x to the base 3. So this we can simplify it as log 10 times x to the base 3, which is log 10x to the base 3. Now using the quotient rule, log 81 divided by 3 to the base 3 can be expressed as log 81 to the base 3 minus log 3 to the base 3. Now here 81 divided by 3 is 27. So in this case we have the log of 27 base 3 is 3, log of 81 base 3 is 4 minus log of 3 to the base 3 is 1, which is a true equation. Now expanding logarithm using quotient rule. We can expand log a divided by 2 to the base 7 as log a to the base 7 minus log 2 to the base 7. And for condensing logarithms using the quotient rule, if you have an expression of a subtraction for two different logarithms with the same base, then we can express these as log x to the power 3 divided by y to the base 4. Here, the first argument can be written in the numerator and the second argument can be written in the denominator with the same base. Now, one important thing to remember is when we compress logarithmic expression using the product rule or the quotient rule, the base of all the logarithm in the expression must be the same. For example, we cannot use the product rule to simplify something like log a to the base 2 plus log y to the base 3. Why we cannot simplify this? Because their base are different. The first logarithmic expression has the base 2 and the second logarithmic expression has base 3. Similarly, we cannot use the quotient rule to simplify something like log a to the base 2 minus log y to the base 3, because again they have different base. To apply product rule or the quotient rule, the base should be same. The third rule is the power rule. Let us see an example with this. Log 4 square to the base 4 can be expressed as 2 times log 4 to the base 4. Now when you check this, there is log 16 to the base 4. 4 square is 16 and 2 times log 4 to the base 4. Log 16 to the base 4 is 2 and log 4 to the base 4 is 1. 2 times 1 is again 2. So the expression is true. Expanding logarithmics using the power rule. Example, log x cubed to the base 2 can be expressed as 3 times log x to the base 2. So that is 3 log x to the base 2. Condensing logarithms using the power rule. So here we have 4 log 2 to the base 5. Number 4 in the front can be taken as the power of the argument. So we have log 2 raised to 4 to the base 5. That is 2 raised to 4 is 16. Therefore log 16 to the base 5. Now there is another important rule, that is the change of the base rule. Suppose we wanted to find the value of expression for log 50 to the base 2. Since 50 is not a rational power of 2, it is difficult to evaluate this without a calculator. We cannot multiply 2 times 2 times 2 any number to get 50. However, most calculators only directly calculate logarithms in base 10 and base e, that is the natural logarithm. So, in order to find the value of log 50 to the base 2, we must change the base of the logarithms first. If you see in the calculator, we only have 2 types of logarithm. That is normal log and another one is ln. So normal log, log is log with the base 10 and the ln is the natural log, which is the log of e. E is a constant number. We can change the base of any logarithm by using the following rules. Here if we have something like log a to the base b and we cannot solve it, we cannot have a rational value for this one. So in this case we can change the base to x. When you change the base to x, we can write it as log a to the base x divided by log b to the base x. Here the original argument will take the argument in the numerator and the original base will take the argument place in the denominator. When using this property, we can choose to change the logarithm to any base x. So we can take any base of x. But since in calculator we have the base e and the base 10, so it will be easier for us to take it as base 10. Example, let us evaluate log 50 to the base 2. So let's change the base of log 50 to the base 2 to 10. Now that is log 50 to the base 2 can be rewritten as log 50 to the base 10 divided by log 2 to the base 10. We are changing the base from 2 to 10. And in this case, the original argument 50 is taken as the argument of the numerator. And the original base 2 is taken as the argument of the denominator, log 2 to the base 10. That is, we can express it as log 50 over log 2. Here, log 50 to the base 10 is same as writing log 50. When we don't see any base, that means the base is 10. Punching this log 50 divided by log 10 in the calculator, we will see that it is approximately equal to 5.644. So that is the end of today's lesson. What have we learned today? We learned to relate a logarithmic expression to exponential expression. Then we learned the three properties of logarithms: the product rule, the quotient rule, and the power. Finally, we also learned to change the base of the logarithm. That's all for this video. Thank you very much. Let us catch up in the next video.